Welcome back to Engineering Vibrations 1, an introduction to single degree of freedom systems. This is Module 2, and in this module, the learning outcomes are to define vibrations, to list the topics that we're going to cover in this course, and to develop the first of 3 system elements that we'll be using in the course, this one being mass, which is used for modeling vibratory systems. The other 2 elements we'll talk about in future modules are springs and dampers. So what is vibrations? Well, it's an oscillatory motion of a body or a system of bodies. And the following video clips show vibrations. These are rather large vibrations, one being a bungee jump of a person jumping with a bungee, and the other one being that grain elevator that we looked at last time, which is oscillating up and down to separate the grain. And so that gives you an idea of real-world vibrations applications. Let's now look at the topics in the course. So we'll start off with an actual system like that, and I'll actually model those systems that I just talked about, and they have some sort of an input. In the case of the grain elevator, it had a forced input from an engine. In the case of the bungee jump, it started out with some initial conditions and vibrated from there. It was what we call a free vibration system. So inputs can be of various kinds. You can have initial conditions. You can have free transient vibrations. Or you can have things like an applied force or harmonic force, like we would see in the grain elevator. And some other ways of inducing input would be base excitation, a rotating imbalance in the motor system. And the other initial condition that we're going to talk about near the end of the course is using the convolution integral. And so we'll cover all these as we go through my first course, Introduction to Engineering Systems of Motion, and my second system in applications of vibrations. So taking that input, we apply it to the actual system, and we get some vibrations as a result. So we want to come up with a physical model of that system, and we'll use these 3 elements that I'm talking about in this module and the next few modules: springs, masses, and dampers. We're going to model the whole world with springs, masses, and dampers. And so to do that, we're going to make some simplifying assumptions on our actual system. We're going to look at lump characteristics, and you'll learn more about that as we go along. We're going to look only at linear systems. All systems are nonlinear, but we're going to simplify this some and look at just linear systems. And we're going to look at constant parameters rather than parameters that vary with time. Now, this will be a good starting point, a good way of analyzing the systems. Obviously, if you want to get more in depth, you're going to have a more complex model. But in this course, these are the assumptions we're going to make. And that will lead us to taking an actual system to a physical model. And we can model systems as single degree of freedom systems or multiple degree of freedom systems. As I said in the introduction, my first and second courses are going to look at single degree of freedom systems, and my third course is going to look at multiple degree of freedom systems. The next topic will be then to take that physical model and put it into a mathematical model that we can study. And to do that, we're going to use physical laws like Newton-Euler equations, F equals ma, for instance, Lagrange's equations, energy methods, and that will allow us to come up with a mathematical model which will be in the form of a differential equation. There it is, the differential equation of motion, which I will abbreviate throughout the course as the DEOM. And so we're going to have to put in a mathematical input that will excite the mathematical model of our actual system, and it will model the conditions that I show above: initial conditions, applied force, base excitation, etc. And after we input that to our differential equation, we'll get some response solution. And that's going to help us to analyze the system, to perhaps design it differently, to do all sorts of things. So that can either be in the form of a technical free steady state solution, or technical free solution, or a transient solution, or some sort of a steady state force solution for those inputs that are a forcing function. And when we get those two results, we can test and compare. Perhaps the mathematical model is not giving us the results that we would like, and so then we would go back and update the model if necessary and continue the process as an iteration. So there's a great overview, and I'll refer back to this throughout the course, of the overall topics in the course. I often talk about this as being the forest instead of the trees. We're going to get lost in the trees a little bit here as we go through and take any of these topics individually, but I'll always refer back to this so you can see the big picture of why we're doing the things we're doing. So for the system elements, the first system element I want to talk about in this module is mass. And these are objects or rigid bodies that have inertial properties. And so mass is given the symbol m, and we say it's a resistance to linear acceleration. So we see it in the Newton-Euler equations, F equals ma, the mass is included there. And it's given in units of kilograms or pounds second squared per foot, which is called slugs. Kilograms is the International System of Units, or the SI System of Units. Pounds second squared per foot, or which is equal to slugs, are from the English System of Units. And I'll use both systems in this course because in reality, even though it's not used around the world, both systems are used a lot in the United States. The second mass or inertial property is the mass moment of inertia I, which is a resistance to angular acceleration for a body undergoing rotational motion. In this case, this is our Newton-Euler equation for that. Sum of the moments equals I alpha instead of sum of the forces equals ma. Moments are analogous to forces. I is analogous to m, and the angular acceleration is analogous to the linear acceleration in these two equations. So you can see there's a complete analogy there. The units for I are kilograms meters squared and slugs feet squared. And I want to go back to an earlier module that I did in an earlier course on 2D dynamics, which gives a little bit more background and more details into these concepts of mass and mass moment of inertia. With F equals ma, if I have a body, let's say I have a small automobile and I push it with a certain amount of force. Let's say I'm able to push it with 150-pound force. Okay, so for a small automobile, if I push that with 150-pound force, and then I compare it to pushing a large vehicle with a lot of mass with the same 150-pound force, think to yourself, which vehicle will accelerate the fastest? And it should be obvious to you that the smaller vehicle, if you're applying the same force, will accelerate faster than the larger vehicle. So mass is sort of like a measure of resistance to linear acceleration. We can say the same thing for sum of the moments equals I alpha. Mass moment of inertia is a resistance to angular acceleration given the same amount of moment. And so I want to do a little demonstration here for that. I am the body now. The z-axis is going to go through my head down through the platform. I'm going to have to start out a whole lot of mass that's away from the axis. I'm going to keep my arms out. So I've got a lot of mass moment inertia, a lot of mass located far from my axis of rotation. And so then I'm going to bring my arms in, which is going to reduce my mass moment inertia because I have less mass away from the axis of rotation, which should allow me to increase my angular acceleration. And so we'll go ahead and do a demo here. And so I'm going around, and when I pull my arms in, I go faster. We'll do that one more time. Maybe not quite so fast. That's all right. But all right, go ahead. There we go. And so I spin, and then I speed up when I pull my hands in. And now I'm dizzy. That's all right. So that concludes this module. where we had 3 outcomes. We defined vibrations, we listed the topics in the course, and we developed the first of the 3 system elements that we're going to use in the course, mass, as we model vibratory systems. So I hope you're enjoying the course, and we'll move on to the next module.